Also here we are producing this enormous flood of data streams. Okay.
You are recording.
Hmm?
You are being.
I am now on air. Okay. So, mathematical aspects of local versus global risk assessment. So here was the agenda. We have done about one half. The locally law invariant case, we have not yet really fully applied it, but we have done the key argument, very general, that consistency together with law invariance is very strong. It boils things down to the entropic case. Okay, we are also going to need a nonlinear extension of martingale convergence as another tool. So let's first take care of that. So that is done in the last of the three papers on which these two lectures are based, joint work with Irina Penner, which is going to appear in a volume on stochastic analysis in honor of Fukushima in Japan. Okay, so the standard setting for martingale convergence, both forwards and backwards. You have a filtration. Let's index it by the full discrete time axis. So we only need discrete time. So a filtration, increasing sigma fields. And passing to infinity, we have the sigma field f infinity. And going back to the infinite past, we have the intersection of all these sigma fields f minus infinity. Now, if we consider conditional expectations, yeah, I write here eta n for the conditional expectation of minus x, just to be able to say this is a special linear case of a conditional convex risk measure as defined below, due to the minus sign. Okay, then this conditional expectation, as you all know, due to the projectivity of conditional expectations, is consistent in this sense. And Dup's basic convergence theorems say that as you pass to infinity, these conditional expectations converge, and they converge to the conditional expectation of minus x with respect to the limiting sigma field. And it's the same thing in the backwards direction. So it's a kind of asymptotic precision in both directions, forward and backwards. Now our aim in this short excursion is to extend this to convex risk measures. So the question is, how do convex risk measures conditionally behave along filtrations, both increasing and decreasing? So now we need conditional convex risk measures, so a nonlinear extension of conditional expectations. So technically, we fix a probability space, and for each bounded random variable on this probability space, we associate something conditional risk of a random variable x, which will be Fn measurable. So it will be an element in this smaller space built on the smaller probability space, or smaller in terms of the sigma field. And that is supposed to be monotone, an analogy to the unconditional case, cache invariant in a conditional sense. So at each time n, if you add capital Mn, but that can now depend on the information we have, so that will be Fn measurable, you can pull it out. And same for convexity, you require it now in a conditional sense, which means that the convex weights are allowed to depend on the information you have, so Fn measurable. And then, as in the unconditional case, you can interpret it as a capital requirement. it's the smallest amount, but the amount is now a random variable depending on the past Fn. So you must take an essential infimum such that x plus mn is acceptable, and the acceptance set of rho n at time n are simply those random variables where rho n of z is non-positive. Okay, and then very simply you have this representation. And typically you also have a dual representation or conditionally. So you take measures q, you penalize them conditionally. So you take the worst conditional expected loss under q over all acceptable positions at time n. So that's now the penalty function, which is actually now for a given q a random variable, and then you have typically this representation. So the penalty functions are now, as n varies for a fixed q, a stochastic process. And the question is, what are properties of this stochastic process? Now, necessary and sufficient for this representation to hold is again a little bit of regularity in the form of a Fatou property. So whenever you have almost sure convergence, uniformly bounded, you have almost surely that rho n of x is smaller than or equal the limit inferior. We are going to use later on a stronger property, the Lebesgue property, which would require that in such a situation actually things converge. Okay, but for the dual representation in its conditional form, this is necessary and sufficient, the Fatou property. Yeah, this was shown by Detlefs and Scandalo at that time. Also, Scandalo was doing his PhD thesis with Fritelli in Mailand, and Detlefsen was one of our diploma students in Berlin, and they independently did the same thing. Then they found out they were both a little bit frustrated, but then I said, no, you must see this in a positive sense. You must write now a joint paper on this. So they visited each other mutually in Berlin and Milan, and they wrote a joint paper in finance and stochastics. So that was resolved. In the special coherent case, rho n would also be positively homogeneous. Then the representation boils down to the essential supremum of conditional expectations over a certain class of measures. If in addition rho n is required to be co-monotonic, I won't even go into this, then you can, if you like, interpret it as a Schottky integral of the loss with respect to a conditional capacity defined in this way. So it's a link to probabilistic potential theory. And in fact, there is recent in that community interest in conditional Schottky integrals, but that's pretty recent. This is not a classical topic. Yeah.
So you said if you just apply everything conditionally, you take conditional expectation,
Yes.
worst case conditional expectation,
Yes.
then it's consistent, time consistent.
No, I have not yet mentioned consistency. No. Now comes consistency. Now here's a strong definition of consistency. Also thinking in terms of time, if you know that tomorrow, no matter what will happen up to then, the capital requirement for x will be less, then today it also should be in this relation. This translates into the recursiveness form of strong consistency, which we had put down already yesterday. And in terms of acceptability, it is equivalent to the fact that the acceptance sets split in this form. So an is larger than an plus 1. So it's an plus 1 plus. So it means this is the class of sums. There's one component here and one component here. And this here is the acceptance set, but the myopic acceptance set, just looking one step ahead. So it's AN acceptable, but only for random variables which only depend up to what happens until tomorrow. So that is the usual consistency. So to distinguish, we might say strong consistency. Here is one possible relaxation. You require the consistency condition up there, not for any pair x and y, but just for any x and as benchmark 0. So much weaker condition. That's weak consistency. And that simply translates into the fact that the acceptance sets AN plus 1 is contained in AN, so the acceptance sets will decrease. And that is equivalent, actually. It implies that you have a super martingale inequality for the penalty function. So the penalty functions form a stochastic process.
Sorry,
Yeah.
so the acceptance set decrease, that's because you fix the horizon and all the x and y's have the same horizon, they have the same maturity.
Yeah, I'm talking.
But this is, so that's why they decrease, it's not.
No, they decrease.
Yeah, they
Yeah,
decrease
yeah.
because as you go
Yeah, I
forward.
admit any random variable
Yeah, but-
up to.
This is learning about a fixed state. This isn't over time, things are happening
Yeah,
dynamically.
but that's.
This is just learning, it's not
Yeah, but
anything
that's
about.
important because you fix the horizon, so as you go forward, as you get closer to the horizon.
Yeah, I have not fixed the horizon.
Well, yeah, because the x's are always fixed.
Not for me, but
Yeah,
we
X
could.
is a
Oh,
fixed-
yeah, we could. So this means for any x,
Yeah, but x, but how do you interpret x? X, you have to compare x and y, you do sums.
Yeah, yeah.
So if x and y are claims play the different maturities, the only way you can put x plus y, makes sense, is that you compute them in discounted values or you compound
Yeah,
them up
they
to
are-
the same date. So implicitly, the fact that you write x plus y means that you're counting them with a numerator which is based on the same date, discounted to the same date. So when you go forward
Yes.
in time, the maturity of each claim is shrinking, and therefore you compare rho of x always to the same threshold, 0.
Yes.
But if, for example, if my tolerance for a 10-day value at risk is 1 billion, my tolerance for 5-day value at risk is not 1 billion, it's less. So when n goes forward, I should change the threshold for the acceptance set. Otherwise, it's not stationary. You see, for example, let's think about the following case. There's an options portfolio, and every 3 months you have a maturity. So in between the two maturities, the option maturity shrinks to 0, and then you enter a new position, 3 months, 0, and so on. So if I'm 1 week before the maturity, I cannot but define my tolerance for risk for the loss level in the same way that if I'm 3 months before the maturity, because otherwise the same portfolio will be considered too risky depending on the date I look at it. So I think hidden here is that the way you add x and y's, there is a fixed maturity, but when you go forward in time, you shrink the maturity. In the static case, it doesn't matter. But here it does matter, I think.
Okay, so I would have to think a little about that. So do you suggest to?
It would certainly be hard to get this condition to hold, that you know now that tomorrow, no matter what happens. I mean, if in the scenario you described, where you have, let's say you have a rolling window and you're looking
Yeah,
at value risk out 20 days, and that you're always required to do that, then if you are looking today it's unlikely that you'll say, okay, in 5 days, no matter what happens, I'm going to do this. So this condition would be hard to
Yeah, I mean,
satisfy.
but even before we talk about this condition, I'm just saying that when you put time in the picture, there is the problem that if you take a fixed set of random variables and you allow them to be added together, it means implicitly you're discounting them in the same way. You're discounting to the same date. So then that date, whatever it is, can be 0, capital T, whatever you like. When you move time forward,
okay,
you
no,
shrink the horizon.
Yeah.
So we are talking about risk computed at different horizons, whereas usually you think about a fixed risk horizon and you move in time. This is how you do it.
So it's already a big limitation at point in time that this literature imposes that the risk measure should be a scalar. And you're saying that that's much more severe restriction even when you have an intertemporal context.
Yeah, I mean, it boils down to the difficult problem of comparing streams of cash flows at different points in time. Basically, if you want to do that in a dynamic context, what you really want to do is that you have streams of cash flows at different points in time.
Yes.
And somehow you are collapsing them into a random variable. So you can do that by discounting, but discounting requires fixing the horizon implicitly. And once you fix that horizon, when you move n forward, you shrink your relative horizon. So maybe that's why an is increasing. But
Yeah,
do you want
okay,
it
so
to
but that's a
decrease?
different kind of argument. Okay, I would have to think about that more carefully. Okay, in this form, anyway, we get Q supermartingale property of the successive penalties. At least this inequality, these things are non-negative if the risk measures are normalized, and so if we also ensure integrability, then it will be a Q supermartingale, which in a way is like an implicit learning effect because it's supermartingale under Q. So if Q actually drives the situation, then the penalization of Q goes down in the sense of the supermartingale inequality. So that's one thing. Now, strong consistency in this picture is more. It is not only the supermartingale property, but an explicit splitting. So alpha and Q is the conditional expectation plus something, and this something is here. So just looking one step ahead. So that means strong consistency not only gives the Q supermartingale property corresponding to weak consistency, but also fixes the Doob decomposition explicitly. Because that means that alpha and Q is the sum of these differences, which is a martingale difference, and so here we get a martingale, plus the cumulative effect of these additional terms, and that's a predictable increasing process, so that is the Doob decomposition. Yeah, so all this different pieces of this appear in different papers. In particular, what we are going to need is that strong consistency is equivalent also to the following. For each fixed x, if you look at rho n of x plus the penalization for a given measure q, then this process satisfies the supermartingale inequality. And so if for a bounded x rho n of x stays bounded, so but you have to make sure that this also stays bounded to now conclude it's a true supermartingale, and you can apply convergence theorems for supermartingales, and that means that almost surely you get convergence in both directions for the increasing filtration and for the decreasing sigma fields. Now, what about this property of asymptotic precision that we have in the martingale case? In the forward direction, let's define asymptotic safety by saying that the asymptotic capital requirement is enough to cover the loss minus x. So in the end, it will be revealed. Yeah, the f infinity, we can of course also think of a finite deadline, which we approach in a finer and finer way. No? So the limiting situation can actually be a situation at some finite horizon. And the stronger property would be asymptotic precision, that you get equality, so that in the limit you have exactly what is needed. Now this may or may not hold. There are counterexamples in this paper with Irina, and criteria which guarantee one or even the other. But for our purposes here, we need the backwards direction. And in the backwards direction, that is the third reference, this joint paper with Irina Penner, turns out everything like in martingale convergence. The backwards case creates less problems in terms of conditions that are needed than the forward case. So in any case, this limit which exists is a good conditional risk measure with respect to the intersection of the sigma fields, which means the Fatou property holds and the dual representation then holds, because we have the Fatou property. And it's given by the penalty function, which appears as a limit of that super martingale under Q. And consistency is preserved in the limit, which means rho minus infinity is consistent with each risk measure rho n. Okay, in particular, one gets good convergence properties for conditional Choquet integrals, which in that literature I think had not yet been done, the recent literature on conditional Choquet integrals. So now in this talk we want to apply this to spatial risk measures, and there we do not want, as we did here, fix a global reference measure P in order to leave room for the critical phenomena which have to do with non-uniqueness of the measure. Okay, so now back to the spatial setting, which we looked at yesterday. So we have a set of sites. Each site can be in some state S, and so we have a configuration space. For each subset J of I, Fj will denote the sigma field describing what can be observed on that subset J. And the global risk measures we are going to consider will be risk measures on the space of bounded measurable functions on the full, on the configuration space together with a full product sigma field. So we don't fix a global reference measure P here, so we just take risk measure on bounded measurable functions. Later on, at the moment, no risk measure yet. We start conditionally. So at each site, we specify a conditional risk measure. But since we have no reference measure, as in the discussion before, it's like specifying a conditional probability distribution without a reference probability measure. So then you take a kernel. No? So here we take a regular convex risk kernel from this measurable space to this measurable space, which means for any fixed omega, it's simply an absolute risk measure on, xi can be anything, so, but outside, regular means outside of I, this behaves like a Dirac measure. So you can freeze everything outside, and so only the dependence on the i's coordinate matters. Yeah, and for a fixed x, as a function in omega, it should only depend on the outside. So in that sense, risk kernel, like a stochastic kernel from one measurable space to the other. And so this assesses the risk at site I, conditional on the environment of I, which means the situation outside. Well, maybe you only need some neighbors, but in principle, it depends on the outside configuration. So as I said yesterday, it's a conditional, not a marginal approach. And then more generally, let's now take finite subsets of I. I is now, we are going to assume that for problem 2, to which we are coming in a second, that I is infinite. We are doing asymptotics. And so we fix for each finite subset such a regular convex risk kernel. Now, given the environment of V, and the definition is that this family is called the local specification, if we have spatial consistency in this sense. Then I showed you already the classical special linear case where we have conditional probability distributions, and the risk measure simply consists in taking the conditional loss computed with this conditional probability distribution. And so that's the local specification of a random field. For each finite set, we have a probability distribution given the situation outside of that set, and we have spatial consistency for these probability distributions. A nonlinear example is the entropic local specification with some fixed parameter. We checked yesterday that this is indeed consistent, and a priori for each V we could fix the beta depending on V and the outside, but then it turns out to get consistency it must really be the same. Beta depends on V, beta V must be equal to beta W, at least almost surely with respect to the relevant kernel. And so it must then at least depend on the tail field only, no? Or actually be constant. Now the first problem was construction of a local specification from the one side risk measures. So how arbitrarily can we prescribe the conditional risk measures at the single sites? I do not know in general, but in the locally law invariant case, this will come out of what we are going to do. And what we can do also in much more generality is the second problem. Given such a local specification, what is the structure of all global convex risk measures which are consistent with these local conditional risk measures in this sense? So here we think of a large network. We do thermodynamic limit, assuming infinite graph, and we are going to use a construction of that goes back to Dünkel in the following way. So that's the solution now in the linear case of Gibbs measures. Yeah, in the linear case, we have conditional probability distributions, PV, a consistent family. Then let P, calligraphic P, denotes a class of all random fields, all global probability measures, which are consistent with the local conditional probabilities. Phase transition would mean that it's not uniquely determined, the global probability measure. Now then, the question is, what can we say about the structure of that set? So to this end, we introduce the extreme points. This turned out to be the extreme points. but the E could also stand for ergodic. So that's all the probability measures on the big configuration space which satisfy a 0-1 law on the tail field. So F infinity, maybe I should have written minus infinity, because now that's for the tail field long decreasing filtration as we expand the finite V.
So what is this tail? Because
Tail field
in the
is,
previous case,
are all the events which do not depend on any given finite number of coordinates. So these are in a way the macro events which do not depend on. Yeah. And this can be very rich in such an infinite product space. But ergodicity here means that P behaves deterministically on the tail field, satisfies a 0-1 law.
because I'm trying to understand what this is exactly. Because in the previous example, you only had one parameter. So tail field was n goes to infinity.
Yeah, okay, we are going to
Here you can have,
make the connection in a second. Here,
Here you can have
yeah, sure. But
bounded-
this tail field is the same if you do the following. You fix one sequence of increasing a subset such that the union is everything. And then it's also the intersection along that increasing sequence of subsets, which means decreasing sigma fields describing the exterior.
any sequence.
Yeah. The tail field would always be the same. That's a simple exercise to check that that's okay. Now, the Dinkel method gives you an integral representation in the class of global random fields coupled to the tail field in the following sense. There is a way of extending the conditional probability measures for finite subset to a kernel, to a conditional probability distribution given the tail field. So there exists a stochastic kernel from the tail field to the full space, such that each measure p infinity omega is ergodic in that sense. And so that each p in our class of random fields is also consistent with this kernel. So by definition, it's consistent with respect to the finite volume kernels, but also for the tail field you get it. And that means that you can write P in this form, but then this can be interpreted as an integral representation. P is the mixture of measures Q in the class of ergodic measures, namely such measures here, and the mixing measure on this class is the image of P under the map, which goes from omega to the class of extreme points.
I have a naive question.
Yeah.
There's something I'm missing.
Okay.
When we go through the sequence of sigma fields,
Yes.
are we thinking of increasing the size of the network, or are we doing this
No,
over time and we get information?
No. Here, no. At this point, we assume we have already an infinite network, and we are approaching it from inside by finite subsets.
Okay, so it's an infinite, but it's infinite network. And then,
Discrete.
and then when we're looking at increasing set of subnetworks.
Right.
Okay.
And so the
okay.
available information on the outside decreases, and it decreases to the tail field.
Okay, so it's just a fixed network,
Yeah.
but it's
right.
infinite.
It's infinite.
And as we expand that network, so we're conditioning on further and further things,
Right.
then
right.
we get to limit this information in the tail field.
Yeah. Right.
Okay.
And so the essential part of the tail is actually a sub-sigma field, which is countably generated in contrast to the tail field itself, namely the sigma field generated by this map. That's what you need. Now in case, if there's no phase transition, you only have one, then F infinity would be the trivial sigma field, so nothing interesting would happen. But in general, in the case of a phase transition, something happens. It's not a trivial sigma field, but maybe much simpler than the full tail field, and let's call that the Dynkin boundary. And the point is that the Gibbs measures can then be characterized by what they do on the Dynkin boundary, so by their restrictions to the sigma field. And so there is a bijection between the full class of Gibbs measures and probability measures on the Dynkin boundary.
So this 0-1 assumption says that there's not, say, interest rate that everybody sees and it's a function of, that we could be conditioned
Yeah,
on it.
yeah.
There's no macro variables.
Well, there's no macro random.
Yeah, there's no macro randomness under that P. The P, for P, things are deterministic at the macro level. 0-1 law. So any tail measurable random variable would be almost surely constant for such a measure, for such an ergodic measure. So now, so my question, I was carried away here purely by a purely mathematical motivation, namely, is there some analog to that story, which I happen to like already a long time ago, very much, in the nonlinear case of these spatial risk measures? So we fix now a probabilistic picture, the local specification of a random field, as I just described, à la Dobrushin. And we also fix the local specification of a convex risk measure, which will be tied to the underlying probabilistic picture. Now, in the case of local law invariance, we assume that locally, for each environment omega, rho v is law invariant with respect to this conditional probability measure. So that's a strong way of tying these risk measures to the underlying probabilistic picture. Then in the next step, we'll relax that and only require that the null sets are respected. Not law invariance, but respect for the null sets. Yeah, okay, but in the local law invariant case, we have now that for each omega, a picture outside of V, this risk measure will be law invariant with respect to that probability measure. Plus we have consistency. And therefore, we can apply this general theorem I described yesterday and conclude that the situation must be locally entropic. So a priori, so the theorem applied gives you that each conditional risk measure must be of this form. So a priori here, it's just some risk aversion parameter, but then applying again consistency, it must coincide, otherwise it wouldn't work, at least, P almost surely for every random field consistent with these conditional probabilities. And that means that P almost surely, this will be tail measurable because it will only, so this will be measurable with respect to the information outside of V, and that is true for any V as you increase, and therefore it will be tail measurable. And by ergodicity, also the modulo P, so for any random field in this class, it will actually be almost surely equal to the expectation, and so we can take this regularized version now for our parameter. And in this case, we can just as in the Dinkel construction, immediately write down a straightforward, consistent extension of the local risk measure to a conditional risk measure with respect to the tail field. Namely, we simply take that parameter, this tail measurable parameter, and we take the Dinkel kernel and write down the entropic risk measure with respect to that kernel P infinity. So this gives us a conditional risk measure, which then is consistent with the whole family for each fixed omega. And that's the key to the structure problem too, as
So
we are
what is
going to see.
P infinity? What is P infinity exactly?
P infinity was the kernel in the Dinkel construction, the canonical extension of my local conditional probabilities to a conditional probability just with respect to the tail field. And once we are there,
So you mean so initially each of the agents has a view on their on the probabilities given the environment. That's PV. And pi infinity is you need to specify the conditional distribution given the environment and the macro events.
no, only the
Only
macro
macro.
events. Yeah, yeah. So
So it's a
as I
conditional
expand,
distribution
I
given
work with less and less information, and then in the limit I have this P infinity, which, given the tail information, the macro information, gives me a probability measure consistent with the local stuff. And this actually is a very nice risk measure in the sense not only does it have the Fatou property, it also has an effect property with respect to this probability measure for each omega. So it's as nice as you can expect. Now this step, getting down to the tail field, how does this work in general? Beyond local law invariance, so without using that theorem we did yesterday. So now assume only that the null sets are respected, that we have absolute continuity. Then we have a dual representation with some penalty depending on omega. And let's assume that they stay uniformly bounded. In the locally law invariant case, this will be automatic with C equal to 0. And now the question is how we pass to the tail field. Yeah, we simply do something naive at first. We take a fixed sequence expanding to the full thing. We take for each omega the conditional and each given position x, the conditional risk measures, and we take the limb soup. A priori, no reason why it should converge. And this is still a regular convex risk kernel from omega f infinity to omega f, which is consistent, but otherwise not clear whether it has any good properties. Now, to get properties under any given global random field, we use now the nonlinear extension of backwards martingale convergence, which I showed you in the beginning. So it turns out for any global random field, P almost surely this limit actually exists. The limiting object is actually a conditional risk measure in the sense which we had in the first part with respect to a basic probability measure. Now, if you take any P in this class, you will get a conditional risk measure with respect to the tail field and with respect to that measure. And it's nice. It has a Fatou property. And it has a dual representation. And the penalty function is the limit of the local penalty function. So we do now one more regularization step by averaging for each omega with the ergodic measure p infinity omega. And then the result is that we have a regular convex risk kernel from the Dynkin boundary, the essential part of the tail field, to omega f that is consistent with the local family of risk measure and has the Fatou property with respect to the Dynkin kernel p infinity. So an exact analogy, nonlinear analogy to the underlying picture for the Dynkin kernel. And once you have that, you get a representation theorem for nice global risk measures rho of the following form. Let's now focus on global risk measures just on the space M of bounded measurable functions on the full configuration space, which have the Lebesgue property with respect to the class P, which means you get convergence rho xn against rho of x for any uniformly bounded sequence in M such that you have almost sure convergence for any of the measures P in my class of global random fields. And let's define this class of convex risk measures just on the Dynkin boundary, which means here you have a measurable space, you take bounded measurable functions, M hat, the class of bounded measurable functions on the Dynkin boundary, and just a risk measure on the Dynkin boundary. So at the macro level, if you like, the essential part of the tail field. And the L says also Lebesgue property with respect to the global random fields, which, because this means a Lebesgue property with respect to each p infinity omega, they are all ergodic, and that translates into pointwise convergence. So Lebesgue property with respect to pointwise convergence on the Dynkin boundary. And then any rho can be split or represented in the following form. Here there is this conditional risk measure with respect to the Dynkin boundary, this kernel we have constructed. You first apply this kernel. This gives you something depending on the macro situation, so on the Dynkin boundary, and then you apply a risk measure on the Dynkin boundary, the boundary risk, which appeared in the title of one of these three references. Yeah, and here, this of course will simply be the restriction of rho on this much smaller space. Yeah, and this is combined with the conditional risk kernel that we have constructed. And conversely, if each rho infinity, this kernel for each omega has a Lebesgue property, not just Fatou. We have shown it has a Fatou property always, but Lebesgue property depends. We have seen the exponential in the locally law invariant case, where we had explicitly an entropic kernel. That's okay, it has a Lebesgue property. Then we get a full description of the class of global risk measures. That is a one-to-one correspondence between global risk measures in that class and risk measures just on the Dynkin boundary. An exact nonlinear analogy to the one-to-one correspondence between global random fields and the Dynkin kernel, which allows to get a correspondence just to probability measures on the Dynkin boundary. Here, just risk measures on the measurable space, the space of measurable functions on the Dynkin boundary. So, yeah, and in this case, we have the following corollary. A global risk measure, rho, in this class, so with this additional Lebesgue property, is uniquely determined by the local specification of the risk measure through V, if and only if there is no probabilistic phase transition, or an exact equivalence. So on the other hand, if in the underlying picture we have a phase transition, then of course there will also be a phase transition in this class of risk measures. That means the local risk assignment does not determine the overall result.
So in terms of, for example, the regulators task, what this means is that if the regulator has a device for computing the risk of individual banks or sectors,
Right.
this doesn't mean that
Right.
they
Right.
know what's
Right.
going on.
Right. That's kind of just before I come to an attempt at interpretation, which you just already sketched. If I drop the regularity property globally, the Lebesgue property, then it's no longer true. It can be that there is no probabilistic phase transition and yet a multiplicity of global risk measures. And that can be illustrated in the entropic case, but let's skip that. Yeah, let's now. So, what we have done here, we have solved a purely mathematical structure problem, vaguely motivated by the much broader issue of risk analysis in large financial networks. But I got carried away just by the analogy to the classical phase transition stuff. But we then could say something. So it's an example where some questions come up in finance. As a mathematician, you isolate a corresponding mathematical question, and then you get carried away, you do your stuff on strictly mathematical grounds. That's what has happened here. And then, of course, in the end, the question is there any meaning for what you did in the other direction? Now, I don't make any claims at this stage, as I warned you right in the beginning. But the message is exactly what you just started to explain, that local, even conditional, versus just marginal. Just marginal is clear that if you just do marginal local analysis, it won't determine what's going on if it's not a completely IID situation. So even conditional, as we do here, may not suffice to capture all sources of the aggregate systemic risk. So in nonlinear analogy to the probabilistic analysis of phase transitions, where you specify locally through an interaction potential the dependence of nodes on their environment, but this does not tell you what will globally happen in the case of a phase transition. Ising model, locally, you know exactly how the sites behave given the environment, but overall there are different states and it may flip between these states in the sense of a phase transition.
But here there's no flipping between states.
No dynamics yet. That would like passing from the Ising model to the Glauber model, now introducing a dynamics on this. No, I have not yet.
Okay, but here, when you say that this tail, the signal field is, you have this 0-1 law, basically it means that under this condition, macro events there's no uncertainty in macro events.
No, there is uncertainty because I do not know which of the ergodic measures will be active.
Yeah, so in a static setting,
I do not know that.
You're in one of the global,
one
of the global phases. So in a given phase, the macro events are not uncertain.
No, there will be a law of large numbers.
So now you
right.
could say, okay, there are some macro variables which are determined by other external factors. For example, the central bank will change interest rate or some other factors which are not in the network, then you can do this conditionally. So there's some macro variable, and
Yeah.
everybody looks at that macro variable to compute the
Yeah.
risk. So conditionally, you would still have this. So this means in this model, the macro uncertainty can drive risk of agents, but not the other way around, because
Yeah.
there's a one-way thing.
Yeah.
Whereas in in Julius's talk, they were trying to do the opposite, right? They were trying to explain the volatility of macro variables through the interaction of individual sectors or producers or so on. So I'm trying to see what's the link between.
No, the first, in this picture, there are no external sources.
Yeah, yeah,
This
I understand there's no
indeterminacy
external.
is created internally.
Yeah, I understand.
Yeah.
But suppose you drive some macro variable
Yes?
by an external process.
Yeah.
It's completely outside of this.
Right?
picture.
Yeah,
For
that would
example-
mean pinning down one of the possible.
Yeah,
global-
and then this moves, so
Yeah.
this external variable moves from an exogenous source,
Yeah.
okay, not within the network. So
Okay.
the network is a banking network, so you're describing the risk of banks given the situation of other banks, and they have a view on this. But then the risk also depends on the price of oil.
Yeah.
This is
Yeah.
not within the network. The network
Okay,
cannot determine
yeah,
this.
okay,
Well,
okay.
it is not true.
Yeah,
That's the
yeah,
that's
yeah,
the
yeah,
thing.
yeah.
And then in this model, this is in the tail, because everybody will depend on that, but nobody
Yeah,
will determine.
Yeah.
So this will be driven by some external random process. So for each given state of this external variable, you will have your setting, and changing this external variable can move you from one equilibrium to another. But that's, so the macro risk can only be driven by a macro source.
Yes.
Yeah.
Yes. Yes.
But
Yeah.
But in the models, for example, that Julius was describing, long cluster and so on, that's what they try to explain is the level of macro volatility in macro variables through some interaction in the network uncertainty in production or individual uncertainty.
Yeah, maybe good.
So I don't understand what the connection is. So here,
So just if I may interrupt, the question you mentioned that the law of large numbers applies, but in fact, when there is this local interaction, I mean, what is understood is that it doesn't apply.
Yeah. Right.
Yeah.
Because
So
for
that's
each
precisely the source of.
for each ergodic
aggregate-
measure, it would apply, but you have several. And so the limit, if it's stationary enough, the law of large number would be there in the sense that the limit exists, but the limit is not determinate. Only if you pin down one of the extremal measures, then it gives you a deterministic number.
Mhm.
But it remains a random variable. The averaging is still uncertain at the global level.
yeah, I understand, but
Yeah.
there are many ways for the law of large numbers not to apply. So this is the second
Yeah.
one. So somewhere in your analysis, you assume that what you call the tail sigma field is only contains non-random events.
No, I don't assume it.
No?
No,
So
no, no,
what
no,
does that-
this is just, no. But that's a definition of those global random fields which have that property, which satisfy a 0-1
Yeah,
law
but those
on the
global
table.
random
But I
shifts
don't
are the
assume
only
anything.
possible equilibrium.
Hmm?
Those are the only possible.
Yeah, but there are
equilibrium.
several.
Yes,
So
I
since you
understand.
do not know,
Yeah, so
Yeah,
what you're saying
There are
is that,
several, but you're
Yeah.
always in one of them. There's,
yeah, and
No,
what you were suggesting
you
is
can
it's
be in a
it's
mixture.
the macro variables that are not being considered in the model that are shifting between these
yes,
equilibriums.
yes. So the only way.
That's another level
Yeah,
up.
So you have several possible global equilibrium.
Yes.
We understand that.
yeah.
But in this
And-
picture, the only mechanism which can shift you from one to another, which can then cause macro uncertainty, is some global variable.
Yeah, no, but you
The
can
agents
also
cannot
have,
shift
no, no,
it,
it's
no?
not true that you are necessarily in one global extremal,
mixture, in
any mixture,
Yes, but
that
in
means,
any mixture,
yeah,
the macro variables are non-random.
right, right, right.
So now, so if you look at, if you're in that phase, you look at the macro variables, you don't see any volatility. The only way you will see volatility is when you shift from one of these global
No,
states
but
to
if you have a
another.
mixture, it's still uh, not determined at the
I
macro
have a
level.
random mixture.
So the mixture means,
This
The
mixing
coexistence
probability.
of several
Of variables,
phases
yeah.
in physical jargon.
so
Yeah.
so a mixture, for example, if you have a macro variable which has value A in phase A and B in phase B,
Yeah,
The
then with
mixture
some
means it has a
probability you
Bernoulli
see A, with some
distribution now.
probability you
Okay.
see B. Yeah.
so that's where the macro
Yeah,
is.
yeah, right. Okay, thank you. Do I have to do anything here, like turning it on? Ah, this here.